Thanks very much, Tom. I'm Carl Schultz from LunarG, and I'm here today to tell you a little bit about a tool that some of the guys at LunarG have been putting a lot of work into lately. It's essentially the Vulkan version of vkTrace. It's generally used for capturing Vulkan activity at the API level and then being able to play it back. Mark, the previous speaker, did mention another tool for debugging Vulkan called RenderDoc, which is similar. RenderDoc collects a snapshot of like one frame, which is similar to what vkTrace does, but vkTrace captures many frames and writes them into a vkTrace file. So let's take a look at what vkTrace and replay are all about. vkTrace is the primary tool for collecting the data. It essentially records Vulkan commands and writes them to a binary vkTrace file. These files can be pretty large. They can be gigabytes if your application's running for a long time and doing a lot of things. vkreplay is a Vulkan application in itself, and it reads the binary trace file and just plays back the commands. This tool is shipped in the LunarG SDK. I forgot to put that on the slide, but you can also find it on the Vulkan Tools GitHub repo. So when would you use this tool? If you've got an application that's kind of hard to set up, or you don't really want to give it to anyone yet, or if it's top secret or for whatever reason, or just hard to deal with, you can use it to go ahead and capture some application sequences for later playback. It's a lot easier to play back a vkTrace file than it would be to start up the application in some cases. Like you might want to just show somebody, hey, here's what my application does, but you don't want to make them install the whole thing. So it's kind of you could use it kind of like as a demo tool. A lot of the other applications depend on where your place is in the Vulkan ecosystem. Like if you're interested in drivers, like you're debugging drivers or developing them, it's super useful for creating a bunch of traces. So you can trace a bunch of applications just once and then keep the trace files around and then play them back when you're ready to use them. Also, if you find a bug in a driver, I'm hoping someday they'll say, hey, send us a vkTrace dump of your application so we can play it back and run it through our driver and see what's going on. Vulkan is not easy to trace compared to like OpenGL, because in OpenGL, everything goes through the API. With Vulkan, because it's an explicit API, low level of abstraction, close to the hardware, the portability of vkTrace files can differ across drivers and different types of hardware. We'll talk more about that later. Here's a picture of what vkTrace looks like. Essentially, it takes your application and starts it off as a sub-process, but before it does that, it sets an environment variable. Someone asked about instance and device layers, and this is an example of where you only have to set the instance layer because the device layers are deprecated. So we just set the environment to turn on the vkTrace layer, and the output goes out to a file. And then you can see the command invocation that's how you would trace the cube program, write the output to a vkTrace file, and then play it back. vkTrace can also run server mode if that makes sense for you. You can put the server on a different device and send the data over a socket connection and record the file on a different machine. Here's the command syntax. I'm not going to read the whole thing to you, but that's just a summary of what all the various options are. Note that you can take screenshots, which are useful if you want to do a screenshot compare between a trace file when you recorded it and a trace file when you play it back. And vkreplay similar. And if you're going to make this work over a network, there's an extra environment variable you set to specify the IP address of the machine that's running the server. It's probably not a lot of security here, and so it's hopefully you're just doing this on your internal networks because tons of data are flying across anyway. If you want to, there's a few options you can have on vkreplay to change what you see. In this case, you can play the trace file over and over again 100 times at a loop. So if you're setting up a demo for somebody and just wanted to sit there and play over and over, that's pretty easy to do. vkreplay also lets you select frames to play back. One caution is that when you collect the trace, you have to make sure that you don't cancel the program while it's in the middle of doing something. Like if it's in the middle of a frame and it's half done with the frame, and then you capture that in a trace file and you don't have the rest of the frame in the trace file, and you try to loop it, some really weird things could happen. So when you're tracing a program, try to make sure you terminate the trace program, or the program under trace, cleanly. There's also Android support. There's a few specific things you have to do today for Android, and the documentation for that can also be found on Vulkan tools. I'm not that familiar with the Android development environment, but these notes should help you, because this stuff does work on Android really nicely as well. One tracing challenge that we have with vkTrace is host memory rights to mapped device memory. So as we've been telling you all day, you've got to take more responsibility and do more work in your application, do things that the driver used to do for you. So with something like GL, if you wanted to upload a texture, GL knows what you're doing all the time, and it can trace it pretty easily. In this case, an application might allocate some device memory, map it, and then use the host CPU to copy or populate that memory. And there's no way for an API-based trace program to capture that activity. So there are some kind of tricks in place, like if you go and unmap the memory, we'll take that mapped memory and write it out to the trace file. But if it's also possible and legal for your application to not bother to unmap that memory before it gets used by the GPU. So we have a few things we had to add to vkTrace to help address this, and we kind of call this loosely persistently mapped buffers. So basically, we have some mechanisms in place to detect when the application is dirty to page or written to it. On Linux, we use the kernel page map facilities to detect dirty pages, and we write those to the trace file. And then on Windows, we use a similar thing called PageGuard, which is more or less serves the same purpose. And Android's going to be adding similar capabilities shortly. We'll probably follow the model on Linux, not too surprisingly. And then, this is one of these things, again, that's hard to do in Vulkan. So, and if your application has a ton of mapped memory and it's constantly modifying it, it could make your trace file really big. So that's just something to watch out for. You can minimize the amount of mapped memory if you can and try to reduce the time that it's mapped. But it's kind of, we really don't want people to change their applications just to make the trace tool happy, but sometimes it's necessary. So you might consider adding an option to your program to do periodic flushes to get that memory out into the trace file. Cross-platform trace replays comes up a lot, and this again is one of the tricky things to do in Vulkan because of the low level of the abstraction. It's so low level that a lot of the details about the hardware make it into the trace file, so that when you play it back on a machine that's a lot different, they may not make sense. Also, applications tend to change their behavior depending on what hardware they're running on. Like they might detect that the GPU, there's a single queue for both GPU and transfer, so it only uses one queue. On another device, the GPU and the transfer might be on separate queue families. And so that creates a real problem. So we've done some work to do those mappings, but basically if you trace something and play it back 5 minutes later, it should always work. But if you take that trace file and move it to a different operating system, and if you've got the same GPU and the same version of the driver, pretty good chance it will work, because we do the window mapping for you. So if you record it on X Windows, play it back on Microsoft Windows, we do the tricks to map from one WSI to another. We've also found that, surprisingly, if you have the same operating system, the same GPU, but a different driver, sometimes driver vendors can update their drivers, and you're out of luck because they've changed something. So it's rare, but it happens. And if the GPUs are different, well, a simple program might work. But if you've got something pretty complex, it's hard to say. And so the future coming up, they're adding more features, some being able to do more screenshots along the way. We found it was really useful for testing, for collecting golden images and then playing back and seeing if they compare okay. Because trace files can be big, there'll be a trim option which will let you say, okay, I want a trace file, but please throw away everything but frame number 6. So we keep everything you need up to that, throw away frames 1 through 5, record frame 6, and then throw away the rest. That could help you out with the size. There's also a tool called vkTrace Viewer, which allows you to interactively look at the trace file so you can kind of see what the API is doing. It's not in the SDK yet, but it will be pretty soon. And there's some improvements coming for Android.
Hello, I'm Markus Tavenert from NVIDIA. I'm a dev tech, so this means I'm working all the day with developers, trying to support them, making their graphics application as awesome and efficient as possible, and also working on the driver side to make our driver working as good as possible with your applications. And so one of the things we had starting with Vulkan was it's an C API, which is important to be as portable as possible. But C has quite a few limitations, so we decided to generate something we call Vulkan-HPP to bring the awesomeness of Vulkan to C++, hopefully without any performance implications. So what is Vulkan-HPP? So essentially, we have been able to make an auto-generated C++11 binding for Vulkan. So each time a new spec comes out, we run our generator, we have the new Vulkan C++ API. And yeah, the goal is to integrate features you find in C++11 as seamlessly as possible into Vulkan to give you the feeling of a C++ developer, but giving you all the performance and low-level stuff you get in Vulkan. And so we wanted to improve the error detection at compile time, which was quite a big issue. We had developing our first samples without having any validation layers, and we were missing things. We want to reduce the amount of code you have to type. So Vulkan is very verbose. You have to repeat yourself a lot. You have to initialize a lot of fields and structs. You don't have constructors. We want to simplify the runtime error handling for people who like exceptions, but we don't restrict it to exceptions. And most important, some people say, oh, if you start with C++, you're adding a lot of overhead and it will be slow and everything. I think we managed to make an API which does everything inline, so it's in header only, which shouldn't add any overhead to anything which is critical to your performance. And so, if you're starting to make a new C++ library, you of course start with a namespace. So we are introducing a new namespace vk, where we're adding all symbols. And for each C version of the API, we have a C++ version in the namespace where we stripped all vk prefixes, so that you don't have to duplicate the vk prefix at all. And then we started, okay, the interesting part is compile time error detection. If you look at this small piece of code, there are a few places we hit multiple times, and we've seen at other places multiple times, like people forget to put the S-type correct in the struct. For the flags, there are no safeties, and some flags are not 100% sure. For some flags, you don't know, okay, is this the right flag for this parameter? Because the names are similar, the compiler won't tell you in the C API. And finally, if you're initializing your struct, each line by line, you might forget a field, and the compiler doesn't tell it to you, and you are debugging and wondering, why the hell is the code not working? So in most of the times, 0 as value is reasonable in Vulkan, but not always, and you get some random bugs. You don't know what's happening. And so for the type safety, C++11 has scope enums instead of the normal ones, and those are type safe. So we took all the enums in the Vulkan API and created a scoped enum for each type. And for the values, we stripped the vk prefix. We took the infix for the class name as upper camel case. And finally, the suffix is actual enum name, so that you have nearly the same string in the C++ API as in the C API. But since some enums started with numbers, we had to add a prefix. And we decided to use E for enum. And to be consistent, we used it everywhere, not just where numbers are. Some people like it, some don't, but this seems like a reasonable choice. The next interesting things are flags. Flags in Vulkan are enums. You use OR to combine them to a new value. And if you have scoped enums, you can't use operators like AND and OR anymore because they're type safe. You cannot just randomly generate a new enum somehow. But we've been able to come around this limitation by implementing a class, flex, obviously, where you pass in the type, so the type of flex, and the internal type in Vulkan. And for the bits, we did something similar like for the enums, so with regards to renaming. And we have some using declaration, so like qflex. And this flex class allows you to do nearly everything you can do on the C flex. So you can just initialize a flex object, and yeah, no bits are set by default. You can assign some enum, so you can OR them like you do in C. You can use a compound assignment operator if you want to. You can test if any bit is set or if a special bit is set, if a bit is not set. So if you have to pass flex and you don't say, I don't want to have any bit set, in C API you write 0. We haven't found a 100% compatible way to accept only the number 0. So the most nearest one would be null pointer, which accepts also 0. But you can pass just curly braces instead of the 0, and you're passing no bit set. And finally, we also support the bitwise operator for not. And this one inverts only the bits which are known by the flex. So not all of them, so you have always invalid flex object. And so with type safety on the good way, we decided, okay, next we go to initialization. So we want to ensure that you initialize all fields, or that you have a way to initialize all fields and have the compiler detect it. And so we created classes for each create info, which get a default constructor, just in case you just don't want to set any field. You get a constructor which gets one parameter for each field in the struct. So if you're using this one, you are enforced to pass each and every field. And then we added a function set, foo, set bar, whatever, so that you can chain multiple set calls on the class for people who like the designated initializer pattern on C99. And yeah, we also can cast to native Vulkan types in case you have to pass a struct to some API or some library which requires native types. And finally, you have direct access to all fields because it makes porting to the C++ API way easier. So first we tried to have only getters and setters, but it turned out if you have some C code and you want to port it to the C++ API, it was too much work to be versus. And yeah, let's have a look. So this is some kind of initialization code. Some of you might have already been seen. And with the C++ API, it gets about half as big, or if you would have very long lines, even smaller with regards to lines of code. And yeah, this way it checks if all the flags are correct. It ensures that you have all parameters set. And yeah, it looks already a little bit nicer and more C++-like-ish. So the next thing, the Vulkan API is object-oriented somehow in a C style. So you have those objects you pass in as first parameter, which like command buffers. And we try to match the style of the object-oriented style with C++. So for each handle, we introduced a new class, and you can call the set functions directly on those handles instead of having to pass them as first parameter. And for this, we have, in this example, a command buffer class, and this one has a conversion format to the C handle in case you have C APIs you have to work with. Yeah, you can assign them. You can check if a handle is valid or invalid. And of course, all functions which would take this handle as first parameter have been added to those classes too. And there's one small issue in the Vulkan API. On 32-bit compilers, the non-dispatchable Vulkan handles are not type safe because it's just a type def to a 64-bit integer. And since we want to ensure that everything's type safe, by default we disabled the implicit conversion between the C API and the C++ API. So you can do a static cast if you want to, or if you're working on a 64-bit platform, and you just want to cross-compile to 32-bit, you can define Vulkan-HPP type-safe conversion, and it will enable implicit conversion also on 32-bit. But yeah, you shouldn't do this unless you have a 64-bit project to detect those errors. The next part is parameter handling. So C++ allows stuff like temporary structs, exceptions, and also me personally, I like having return values if I create an object and not passing in output pointers as parameter. So the problem with the Vulkan API is you have to pass in pointers everywhere, which is quite good for C. But in C++, instead, you want to pass references to objects. So we created a version of each function with references instead of pointers, so to allow some features. And in cases where a parameter is optional, so which means it would expect a null pointer, we had to add some special class optional, which can handle null pointer in addition to a reference, and it passes the null pointer directly to Vulkan. And finally, we made the output value, the fence, in this example, as a return value, because we can return errors by exceptions. But as I said, we don't want to force exceptions onto everyone, because some people really can't use them or don't like them. So we added this nice type def result value type. And so if you have exceptions enabled, we will just return the type. If you have exceptions disabled, we return void if the function doesn't have any return value at all, or return the fence if the function doesn't have a result, or finally, if there's a result and some object like the fence, we return a struct containing both values, and you can use std_tie to assign them directly to your values. On C++ 17, you can even write auto result and value equals something, and you have a single line of code to create it, and you get your error code and the object, which is quite nice. And so let's have a look at the results, what we achieved so far. So instead of having to write multiple lines of code for error checking assertion, you can now write your try-catch block and create your object with a single line of code. And since you usually will have larger code blocks, you try and catch, essentially you reduced 4 lines of code to a single line of code. With regards to exception safety, I will talk about the unique handle later. This one wouldn't be exception safe at all. Another thing, if you're using C++, you might have locations where you're using STL containers like std array or std vector or std initializer list, and you want to pass those to Vulkan, and usually it looks quite ugly because you have to pass a count and the pointer, so you have container size, container data, and we were thinking about, okay, is there a way to detect all places where you have to pass arrays? And yes, so if the Vulkan spec is verbose enough to tell us those locations. So we added some objects, some intermediate object, an array proxy, which takes all kind of arrays and just passes them over, so that you can write something like this instead of the code above. So this one will construct an offset2d object, an extend. Now you have a rectangle, and finally, adding another curly braces makes an initializer list. So you have a single line of code where you just set your scissor instead of constructing the object with a lot of lines of code. And the nice thing, the count and the real data size always match in these cases, because the compiler determines it for you. And the array proxy itself, so it can accept an empty list, it can accept a null pointer, which says, oh, I don't have any data. A single element, like you just pass a rectangle. You can pass a pointer and count pair in case you really have data in this way. You can make it construct an initializer list of multiple rectangles in this case. You can't pass an SD vector or an std array. And now you can pass in all your nice containers into the API. Another thing which is not nice, but in the Vulkan C API, enumeration and queries. Looking at in a code example in the C API, you have to define a few variables, and at least for C++ programs I've seen, all of them used an std vector to store the properties. And then you have to query how many elements is Vulkan going to give me back, so how much space do I have to allocate. And then you are going to resize your container, then you have to query again. And magically, it might happen that in between those two lines of code, something has changed, because whatever. And you might get an incomplete result. So you have to go through the same loop again. And there are like 5 or 10 queries like this. And all of those, so you can type it once, and it's hard to read if you find it. And we have been able to just to implement this automatically. So in Vulkan-HPP, you can just call enumerate instance extension properties, and you will get this loop done by the header for you. Now I will talk about a few utility functions we recently added. Some people like resource acquisition initialization, and I took a look at multiple Vulkan layers of people who wanted to use Vulkan and C++, and all of them really implemented something like a unique pointer on the handles. So we call it unique handle for now. And the problem in Vulkan is you cannot just call destroy on the handle, but you have also to pass the parent object and the allocator if you used one. So you have to do some special work. And we implemented this unique handle and create function for each object you can create. So create something unique. And the unique device works exactly like a unique pointer, so you can just substitute it for now. And in the end, we want to use unique pointer, but there were some implementation issues with one big compiler vendor, which is not always standard conform, but we will solve it hopefully. And once you have unique device, you can work it like a normal pointer. You can create it, you can pass it to other functions. And if it goes out of scope, it will be deleted. You can call release, get, whatever you want. But this one comes at a cost. As I said, we have to store the parent and the allocator. So it's useful to use this one in places where you are initializing and you want to put a big try-catch block around your code and then assign the values afterwards. I wouldn't use it in each and every line of code at all. But a lot of people like it, so we decided it's worth to have it in the header file. And finally, we added some debug functions to string for enums and for flags. So you can call to string on each enum, and you get just the name of the enum without all this fancy stuff around. So for vk result x success, you get x success. And if you call it on some flags, you get all flags which has been set inside this flags one. And that's it. Do you have any questions? Or maybe one more thing. So Vulkan-HPP is part of the Luna GSDK, but you can download the generator on the Khronos website if you want to change it to your needs. Everyone is welcome to do changes or file issues. We are happy to integrate them. And I also started to make something more high level than Vulkan-HPP, which tries to get design patterns into some high level framework like shared pointers, reference counting, resource tracking, sub-allocations. Currently, it's an experimental framework, vkHLF, and I'm not sure where it will go because there's, of course, some additional cost once you do this. And it's definitely not designed for engine designers who want to have the last bit out of Vulkan, but it might be useful for developers who just want to render a few thousand objects and don't want to care about too much fancy tracking. Yeah, that's it.
I work for Google, and I'm working on the SPIR-V specification and the tools to manipulate SPIR-V. I'm going to break the talk into two parts. The first part is about making a SPIR-V module and the key components of a module for making it work with your application. And the second part will be dealing with size if you have large collections of SPIR-V modules and need to manage the size better for those. So first part, making a SPIR-V module. I'm going to start on the lower right part of the picture here, offline or online, but not part of the Vulkan API. You can start with a variety of high-level languages, GLSL, HLSL, or even SPIR-V assembly. And we have compilers and assemblers that can translate these into the SPIR-V binary form. You can also take existing SPIR-V modules and translate them or transform them to other SPIR-V modules to create a SPIR-V module which would ship with your application. So after you make a SPIR-V module, you would distribute with your application, and then online or at runtime, the application can load the module and hand it to the Vulkan API. And then on the target platform, the driver will have a SPIR-V compiler that optimizes and translates the SPIR-V module down to the target architecture for that target device. Today we're not going to, we don't really care what a SPIR-V module looks like or the details inside it, but there are a few components to be aware of that go along with it. And one of these is the capabilities. SPIR-V module declares ahead of time all the capabilities that it needs from the target system, the target hardware. And the Vulkan driver underneath it doesn't have to actually execute the module unless it's capable of supporting all those declared capabilities. Also, specialization constants are being carried along, and we're going to talk more about this later for managing the size of a collection of shaders. That specialization constants let you leave your SPIR-V module somewhat parameterized offline and then wait until it's online to specialize it into specific shaders. Also, a SPIR-V module can hold multiple stages or even multiple entry points per stage. Typically, the tools today are just doing a single complete stage for a single SPIR-V module. It's always the case, though, that a single SPIR-V module has completely linked stages in it. There are no partial stages that require, say, a Vulkan driver to take two SPIR-V modules and link them together at runtime. A single module having a stage in it will be a complete call tree for the entire stage that you load into the driver. And generally, a SPIR-V module is stored as a single file. We're using the convention .spv for the binary representation of it. So there's a one-to-one mapping between a .spv file and what we call a SPIR-V module, which is what you hand to the driver to run. So there are a lot of tools out there. Lots of people are experimenting with different high-level languages or different ways of creating SPIR-V or transforming SPIR-V. I'll touch on these 5 repositories today in GitHub. And basically this slide is a reference that you can come back to for the other projects I'll be talking about in the rest of the talk. So GL-Slang is the main compiler today for translating GLSL into SPIR-V modules. It actually has several components in the repository. One is that's been long-standing there is a Khronos reference validator for GLSL, which helps you verify that your GLSL is portable across platforms for OpenGL or Vulkan or whatever. The newer component is a GLSL to SPIR-V compiler. So it takes in the GLSL and creates the binary.spv module for the SPIR-V. And most recently, we've been creating an HLSL to SPIR-V compiler, which we'll talk more about each of these in a couple slides. There's also a reflection capability. You can get a dump back of the variables and interfaces that the high-level language declared so that you can use that to create sideband information you might want to use in the API to set up interfaces. And something called the remapper, whose primary use is to manage size, and we'll talk more about that later on as well. The remapper is an independent tool, and actually if I go back a slide, we're trying to move it to the SPIR-V tools. It really belongs with SPIR-V tools instead of being part of GL-Slang. Okay, so a few words about compiling GLSL to create SPIR-V. The top line shows an example command line options for using GLSlang to do that. The rules followed for GLSL to create Vulkan are a little bit different than for using GLSL for OpenGL. And the top differences are listed here. One is that in OpenGL you could have individual loose uniforms declared, and in Vulkan you can't do that. So when you're using GLSL to create Vulkan shaders, you want to gather up all your loose uniforms and put them in a block, which then you set from the application as a single buffer. The resources like a uniform buffer or a buffer block, which correspond to an SBO or a UBO or an SSBO, or textures, images, samplers, all these kind of resources need to have binding numbers and descriptor set numbers. The descriptor set numbers default to 0, so you can leave that out if descriptor set 0 is okay, but still in the end they have to have them. Generally you'll do this by using the syntax, the layout binding equals and set equals on your resources in order to give them the numbers you'll refer to from the application. And all in-out variables also need to have a location number. Between stages, the linkage happens between the location numbers and between the application and going into the vertex stage and coming out of the fragment stage. That linkage is done by location number. The capabilities I talked about earlier that are in the SPIR-V file are generated by GLSlang based on seeing functionality that gets used by the shader. So as it's compiling, when it sees particular features used, it emits the declaration for the right capabilities in the SPIR-V module. So that's as opposed to, say, having to declare those yourself in the GLSL, what capabilities you want to use. That all happens automatically. But we are still using the pound version and respecting the pound version from GLSL and ESSL as a way of roughly declaring what capability set you're after. And this also lets you maintain some portability of the same shaders between, say, OpenGL and Vulkan or OpenGL ES and Vulkan by respecting the pound version. The other main differences for OpenGL or OpenGL ES with the pound versions, you declare which one you want. The low P, medium P, and high P precision qualifiers are respected for OpenGLS, but not for desktop OpenGL. In Vulkan, that's different. In Vulkan, the precision qualifiers are always respected. So you can use medium P and low P to get relaxed precision. I think Alon will talk about that again later too. And today, GLSlang is creating a single stage and a single module. It can accept multiple input files, multiple compilation units for the same stage and link them together, but the SPIR-V module it outputs is a fully linked stage with one stage per SPIR-V module. Switching to HLSL, this is a project that's come up in the last year between Google and LunarG and Valve and some input from other ISVs. As of a couple months ago, all SteamVR HLSL shaders were working without modification. And there are additional workloads that use more features that are in the progress of coming up, and the features are getting in place. And we're up to a fair number of ISVs now that are giving input and helping prioritize the features they want to see there. And if you go to the GitHub project, you're welcome to chime in and say, these are the most important HLSL features we need if you have HLSL shaders. HLSL doesn't have descriptor sets or some of the same binding type things that GLSL has. So we added the GLSL syntax to HLSL in order to get that done. Also, if you want to try to run shaders unmodified without having to put the descriptor set numbers and the binding numbers, we've been adding options to control this from the command line. So you can see you can specify sampler binding, or I guess the third line from the bottom lets you auto map binding numbers. And then the options above that let you shift number ranges for samplers, textures, and images in order to control from outside the shader how the resources map to the binding numbers. You can also control entry point names. It can be convenient to specify an alternate entry point name for the API in the shaders versus the actual entry point that was in the shader. So the command line lets you do these types of external manipulations. So that was all kind of command line examples, but you can also use GLSlang as a library. You can hook it into your tool chain and use it all programmatically. So there's a file there that shows the interface, and this is kind of the boilerplate for initializing it. You can create shaders and programs, compile the shaders, link them together inside of a program and create a program, and you can use that as a reference just to get started for doing that. So switching to another repository, that was all about the GLSlang repository. Switching to another repository is the SPIR-V tools repository, and it has a disassembler, an assembler, a validator, and an optimizer in it. The disassembler, some of these are pretty obvious. The disassembler will take the binary file and give you back human readable assembly language. And the reason it's actually worth talking about this is it's written using a reusable library for parsing SPIR-V. And if you ever want to do anything like parse your own SPIR-V or do a transform on SPIR-V yourself, I would highly recommend starting by looking at the disassembler and the interface it uses in there to leverage this generic tool to parse a SPIR-V and make a callback for each instruction into your code. So we don't need everybody like writing their own SPIR-V parser. The assembler takes the exact same form and turns it back into a binary, so you can do round-trip editing. If for some reason you need to modify a little bit the SPIR-V that's generated by a tool or a compiler, you can go through the round trip here and tweak the SPIR-V. The validator is made for validating what's within a single module. There's another validator that gets used in the API, the layers validation, that can look at a module and how it interacts with the rest of the pipeline and do interface validation. But this validator is just the validator for what's inside of a module. And there's a lot of validation you can do in there. It's probably checking about half the things that need to be checked. It's a work in progress, and the other half are underway to get done. And the optimizer is another work in progress. There are a number of transforms in flight right now to make SPIR-V modules smaller or eliminate redundant load stores. Quite a few things are in flight there, but it's also still a work in progress. Shader C is a Google project. It's another repository, and its main thing is to wrap all these other tools and to present it in a way that looks normal for a traditional compiler chain using traditional options. The compilers inside there is GLSLC, so GLSLC and Shader C are kind of used interchangeably. And it has snapshots of these tools that it knows all work together and wraps up into a single tool. If you need to be working on the latest features in GLSlang or developing with GLSlang, then you need to use the GLSlang project. If you're happy with an older snapshot of some of the tools, and it's more important to be dealing with in a more traditional command line setting, or just having a wrapper that connects all these tools together, then you want to use the Shader C project instead. At the moment, Shader C can do pound include functionality, and GLSlang can't, but that will be changing shortly, and GLSlang will also have pound include functionality. This is just some example command lines of using Shader C, and the -E to do pre-processing, or -O to specify optimization. So it all looks quite normal, like a GCC compiler or something for the options. and how you hook everything together. Shader C can also be used in a library form, and this shows the boilerplate way of initializing it and creating objects and using it in library form. I'm not going to talk through this, but you have the slide for reference if you want to pull Shader C into your tool chain. This would be a good starting point. All right, so that was all about creating SPIR-V modules to begin with. I'm going to talk a little bit about managing the size of SPIR-V, especially if you have a large collection of modules. One module, there's not really nothing to worry about. So SPIR-V is verbose. It's designed really to maximize portability and simplicity. So there's some design decisions made as far as instead of having to infer things or guess what things mean, to be quite explicit about it, and that makes it a little bit bigger, but it also meant that we had very easy parsing in a portable way, so that it was, every driver interprets SPIR-V in exactly the same way. And like I said, the individual shaders are small enough. GL slang actually includes some debug information, names, and some other things which can be stripped back out. The remapper has some example ways of stripping that stuff out, and there'll be other things in the SPIR-V tools directory for doing that. Some examples shown there. The real issue is when you have some sort of uber shader or some big shader with lots of ways of parameterizing it, and then generate all the combinatorial kind of explosion ways of setting all those parameters. You end up with a large collection of, say, GLSL shaders that now are each hard-coded to the specific specializations. And then the natural thing to do is to translate each of those individual GLSL shaders into a completely separate SPIR-V module, and then you end up with a really large number of SPIR-V modules. Like I said, this isn't a problem if you just have a few hundred shaders, or you're not doing this kind of combinatorial expansion from an uber shader to a large number of other shaders. So this is just for the large collection case. So the best way of dealing with this is to use some features that are in SPIR-V that help avoid this to begin with. And I'll talk about those in a couple slides. And if that's not sufficient or you're not ready yet to deal with things that way, then I'll talk about some compression techniques at the end of the talk. So two big features in SPIR-V to avoid size issues are to use specialization constants. And the idea there is to not do this offline specialization to begin with. Leave your SPIR-V parameterized, like the uber shader was parameterized, and wait until later to specialize it. And this works for the kind of settings that were, say, constant numbers that had a variety of different values. And I'll go through an example of doing that. And the other way, which the tool sets aren't quite handling yet, is to combine these modules back together into a single module, so that if they all had the same copy of a function and you only need one copy of that function in the module, you don't really need like hundreds of modules each having its own copy of the function. So we're working on linkers that can take all these SPIR-V modules and put them back together again and share code where the code can be shared. So this is showing the syntax in GLSL for creating a specialization constant that lets you generate offline a parameterized SPIR-V module, which then online you can specialize to the specific need that you have. So it's the layout, the constant ID equals 13. The 13 is just a handle that you can use later to refer to this. And the variable size is the parameter in this case, and it has an initial default. If you never come back and specialize it, that's just the value it'll end up having. So you'd put that in your GLSL shader or your HLSL shader. the HLSL can do this as well. And compile it. The SPIR-V module will have these numbers, the 9 and the 13 in it, and distribute the parameterized version with your app. And at runtime, the next page, I'll show you how you can change the constant to a specific value. The cool part about this is that the reason shaders are often specialized with this combinatorial explosion is that the compiler can optimize much better if it knows the actual constant values of things. If it's a loop bound, it can unroll the loop exactly the right number of times, or if it's being used in math or expressions, it can constant propagate and constant fold to constants if it knows it. So this kind of gives you the best of both worlds. By the time it actually executes to render on the screen, it'll be fully optimized as if it were a constant. But when you're distributing it, you're distributing the single parameterized shader. So in Vulkan, this is in section 9.7 of the Vulkan API specification. This is the data structure that's used to set up a specialization constant. And then this is example of filling it out to say, like, for the constant ID 13, I want to change its value to 8. And you do this at runtime to specialize the shader. So if that's not all sufficient, I'll just talk a couple minutes about compression here. If in the end you still have a large collection of shaders that is too, that you want to make smaller, there's a couple points about compression. You can just try compressing it, but there are some things you can do first that make it compress much better. One is if you compress multiple modules together, you'll get better compression. And the other is if you normalize a module to make it more compressible, you'll get better compression. So this is an example of a normalizer, and there's a normalizer in the remapper in GL-Slang, and there's a normalizer in SmallV, which is another project that's out there. If you can normalize a SPIR-V module by creating another SPIR-V module, say for example, like all vec4s end up with the same type ID or something across all the modules, then that makes it easier to compress. So if you normalize to valid SPIR-V modules and then compress it, create a compressed collection of modules, and then distribute that, then on the end user device, you do the decompression, you end up with a bunch of modules that are ready to use. So that's using a normalizer that creates valid SPIR-V. If you want to use a normalizer that does really strange things that can't be executed to SPIR-V, then you can do a little bit better, and that's shown in this picture. And this normalizer takes the SPIR-V module, does some things, whatever it is, odd to it that makes it more compressible, but it doesn't give you SPIR-V. It's some specific form. Then compress that, ship that. Then on the end user system, when you decompress, you get back these modules that have to be denormalized back into SPIR-V. And this can give you higher compression rates at the cost of having to distribute a denormalizer, having a denormalizer there. So it's kind of your choice based on, what the actual situation calls for. Well, here's some command line options that show examples of doing this. The example at the top is using a normalizer that takes valid SPIR-V to valid SPIR-V. So it's using the remapper in GL-Slang to do that. So the remapper is an example normalizer in this case. So that's the normalizer. It compresses everything together, and then you distribute it, and then you decompress it, and you're done. The SmallV project that Aras has done needs a denormalization step, and you can see that project on GitHub to learn more about it. So I've alluded to quite a bit of future work here. We're looking at more optimizations, simplifying the compression tool so it's more just like press a button and you don't have to worry about the details very much, and also merging multiple modules together. So these are things we have planned, and that's the end of my talk. Thanks. want to do questions now about any of this? Yeah. Yeah.
So the question is about HLSL to SPIR-V conversion. What kind of version of HLSL shader do you support? Is it DirectX 9, DirectX 11?
Yeah, it's mostly 10 and 11. There's some differences with 9 that we don't support, and obviously there's some futuristic stuff with 12 that we don't support. But yeah, it's mostly around 10 and 11. Any questions that are more important than lunch are fair game?
Is there any plans for dynamic linking with SPIR-V?
Like linking at runtime when you're executing?
Right, or combining multiple modules together?
Yeah, we want to combine modules together offline. So if you have multiple compilation units forming a single stage in a high-level language, like OpenGL let you do that, we want the high-level language compiler, the front end for that compiler to do that, because the linking rules are often language-specific. So we want multiple compilation units for a single stage to get hooked together by the front end for that language to create a single full stage for SPIR-V all offline. Then if you have multiple SPIR-V modules, each of which contains only complete stages, we still want to link those modules together just to have fewer modules and save space and share functions when they can be shared. So that's linking SPIR-V modules together, or maybe merging is a more correct word, merging the modules together offline. And then online, there's no intention or plan that we'd have to deal with that. It's a simplification issue. Yes. Does that answer the question? Oh.
So this is another question related to HLSL compilation to SPIR-V. So I know that recent HLSL compilers expose property of register spaces for resource bindings. So for example, you can specify a specific register and a register space. Couldn't that be mapped to your descriptor sets
Yes.
as binding on SPIR-V?
Yes, I think we're doing that for the bindings at least, and I think I did this quite a while back. We might have leveraged a syntax there for descriptor sets as well. I think Dan Baker of Oxide suggested a syntax for that. So yeah, there is also a more HLSL specific way of, or looking way of doing that in the language. It just accepts both HLSL way and GLSL way in the parser.
Thank you.
And if the descriptor set one is missing, we should add it. I mean, go check. I can't recall at the moment. I know I did it for bindings. I can't remember about descriptor sets. But we should be able to add back in, or add an HLSL looking like way of specifying the descriptor set. Yep.
Hi. In your talk, you said no loose uniforms. If my shader has them, does the compiler fix that up for me, or does my shader actually take that into account?
For HLSL, it does. So the functionality is there, and HLSL gathers them all up and puts them into the block called $default. For Vulkan, the Vulkan API doesn't understand what that is. So for Vulkan, for GLSL on Vulkan, right now we haven't done that. So
I have to modify my shaders before I give it to your compiler, right? Okay.
Right. Now, if it works, that there's a way of gathering up the loose uniforms in GLSL and giving it a name, and then we can refer to that from the API. That code's all written, so it's just a question of, turning it on and giving it a name for that block. So, yeah, feel free to, request that feature on GitHub, and we can look at whether that works between GLSL and Vulkan. I'm not sure off the top of my head if there's an issue there.
An HLSL, obviously, you can pass semantics across to basically say that this is a position or this is a text chord or whatever, which then you can get runtime information from. Is there a way to do that with the converter?
I missed the very last part.
So one of the useful things in HLSL is when you get reflected data back, it tells you marked up semantics per like attribute, for example. So you know it's a position, you know it's a color, you know it's a whatever. So you can use that for binding. It's something we miss from GLSL, and we have to do our own external markup for that. Is there a way within the HLSL converter to get that information out so you can actually
some of that is part of reflection. Well, we use the semantics, like say SV underscore position. Those obviously get mapped to the correct built-ins in SPIR-V for all. There's like 30 or 40 built-ins. So the stuff that has to be in SPIR-V is getting, taken out of those semantics. The part that doesn't have to be in SPIR-V in the sideband, some of that's getting dropped on the floor, and we're talking about designing a second blob, like the SPIR-V is one blob that comes out, and we're talking about a second blob that might come out that has all the sideband information, like the annotations. And somebody's also contributed to GLSlang a programmable thing that visits the variables and sees what's there, and then you could also use that to do whatever you want to do. But yeah, the part that's actually not strictly needed in the SPIR-V module today is getting dropped on the floor, or some of it can get returned to the reflection information that's there. But yeah, if you have specific, feel free to make specific requests for how to handle that in the GitHub repository.
Hi, I'm wondering about the main advantages of optimizing SPIR-V. Like, I'm assuming that the vendor drivers are going to also do optimizations?
Yes. Yeah, and obviously, Khronos or Google or LunarG don't want to get into any business of doing optimizations that might not be vendor neutral. So the optimizations that are all being considered, their primary purpose is to reduce size, things like load store elimination, possibly inlining. That one gets in a little gray area. So the optimizations are only that we do in that realm are only vendor neutral, and each driver does their own vendor-specific optimizations under the hood. So yeah, and I guess a little bit of subtlety there is right. If there are optimizations that vendors do under the hood, if they're done early, sometimes that still saves time because they degenerate out and quit early at runtime, and yeah, I'll quit there. Yeah.
I was wondering, have you seen any improvement in the runtime compilation speed due to those optimizations?
No, we haven't measured that. I've measured that in similar situations in the past and know that can happen, but that'll be vendor specific measurement too. So we'll stick to vendor neutral optimizations and size reductions for these tool sets.
Basically, you talked about the optimization being vendor, not depending on vendors. How about actually features, things like OpenGL's specific extensions that are needed are used by certain applications. When you are doing the compiling, how are you handling those specific sections, like in GLSlang?
I didn't quite understand all of this. You're asking about supporting GLSL's extensions?
Yep.
Yes.
The specific extensions of OpenGL for certain vendors. You are in GLSlang. Do
right.
you ignore them? Do you?
No, vendors are currently contributing their vendor-specific extensions to GLSlang. So NVIDIA and AMD and others have, they do pull requests that say add my vendor-specific extension, and then we accept those, and that's happening. Yep.